All right, so now let's look at analysis of the Gauss-Seidel method. Now you might remember the Gauss-Seidel method, there's a number of ways that we can write it, but I want to kind of put it in this sort of preconditioning and then using the Richardson iteration framework that we have been looking at. And so one way that we can think about Gauss-Seidel is that we take this system and we precondition with D plus L. So on the left-hand side, we're going to have D plus L inverse times A, and on the right-hand side, we're going to have D plus L minus 1 times B. So now what this means, this would be my L. So if I have my system, Lx is equal to Y, the iteration, we saw that we could write this as xk plus 1 is equal to xk plus b minus lxk. And then the iteration matrix T is going to be equal to, in this case, is going to be equal to I minus L, where L is D plus L inverse times A. Now we can write this a little bit nicer. Notice what's going to happen. I can write I as D plus L inverse times D plus L. So I can write this, I'm going to pull out a D plus L on the outside there. Then I'm on the inside, I'm going to have D plus L, and then plus A like this. The minus sign, that should be a minus sign here. Okay, D plus L inverse times D plus L is the identity matrix, and then D plus L inverse times A gives me this part right here. So over here, I'm going to have D plus L inverse, and notice what's going to happen. A is equal to A plus D plus L. So after you do this difference, you just get minus U. And so the iteration matrix, okay, I'm going to leave this here, but I'm going to erase it. Actually, no, I guess I can just leave it up here. This marker is no longer any good, so let me get rid of it. Sorry if that was too loud. So now the iteration matrix for the Gauss-Seidel, T is equal to minus, because that minus sign there, D plus L inverse times U. And now what we want to do is we want to study the spectral properties of this matrix. In particular, we want to estimate its spectral radius. And we're going to do this more or less directly. And so here's my claim. If A, which is equal to D plus L plus U, is symmetric, and positive definite, PD, positive definite, then the spectral radius of T is less than 1. And let me just remind you what these things mean. Symmetric means that A is equal to A transpose. So what this means, if I can write A as D plus L plus U, where U is a strictly upper triangular part and L is a strictly lower triangular part, then it is the case that U and L are transposes of each other. So U is equal to L transpose, and L is equal to U transpose. Okay, this is just since A transpose is equal to A, the upper part of A transpose is just L transpose, and the lower part of A transpose is U transpose. That's the symmetric part, and the positive definite part means that the inner product x and ax, this is greater than 0. Now really, the way that we probably should write this is like ax and x, the inner product of ax with x is equal to 0, but either way works. And in fact, we're going to use it both ways. Okay, so how can we do this? Well, it's going to be a somewhat, it's a more straightforward argument in the sense that when we computed the spectral radius of the matrix for the Jacobian method, we estimated above by looking at the infinity norm. What we're going to do now is say, let's assume we have some eigenvalue, and then we're going to show that the absolute value of that eigenvalue has to be less than 1. Now, if A, okay, yes, all right. So, yes. So here's what we're going to do. We're going to begin with the following. We're going to say, let's assume we have an eigenvector and an eigenvalue for t. So in other words, let me just write it directly. This means that minus d plus L inverse times u times a vector x is equal to lambda x. And what we're going to show is that if lambda satisfies this equation, then based on the fact that A is symmetric and positive definite, we're going to show that the absolute value, or the modulus of lambda would be the more general thing to say, is less than 1. So we can write this. If I multiply both sides of this equation by d plus L, I'm going to get minus ux is equal to minus ux is equal to lambda times d plus Lx. Okay, so we're going to use this fact. And now what we're going to do is we're going to do the inner product. We're going to look at some inner products. So we're first going to look at the inner product of x with ux. Okay, so notice I have ux here, minus ux is equal to this. So if I look at something like minus, let me see if I put it here, if I put the minus sign here, let's say, the inner product of x with ux, with minus ux, is just going to be the inner product of x with lambda times d plus L times x. So it's going to be the inner product with like this. Or let me do this in 2 steps. So we're going to have x, and then we're going to have lambda times d plus Lx. And let me get more consistent with my arrows over the vector so we know what's going on. Now, lambda is a scalar, so we can pull this out and write it like this, as lambda times x d plus Lx. Okay. Now, here's something important. X and ux. Okay. So I'm going to have to write it. I'm going to write an equation and then erase it. So x is equal to x u transpose x. That's one of the ways to define the transpose. Is that it's the thing that satisfies this equality right here. But u transpose is equal to L. So this is equal to L times Lx. Now for inner products, so for inner products, this is equal to this. If you have standard inner products, if we want to swap the order, then we have to pay a penalty by taking the complex conjugate. But everything we're working with here is real, so the complex conjugates are just equal to each other. So then what this says is the inner product of x with ux is equal to the inner product of x with Lx. So in other words, this left-hand side here, so copy that down if you want to, but this left-hand side here I can write in the following way. Okay, so this left-hand side here I can write as x comma minus Lx. Okay, and similarly over here, this is going to be L. I can replace that L with a U, because if you do x, the inner product of x with Lx, it's the same as the inner product of x with ux. And that's based on the symmetry properties. So this is what we have here. And then just for ease of notation, I'm going to bring the minus sign out here, and I'm going to bring the minus sign out here. Now what I'm going to do next is add these 2 equations together. Okay, I'm going to add these 2 equations together. So over here on the left-hand side, I'm going to have minus x u plus Lx. And what's going to happen over here when I add them together? Sorry, I'm being random about where the arrows go. What's going to happen when I add these two together? Well, I'm going to have this matrix D plus L plus D plus U. Now, D plus L plus U, that's A. So this is just A plus D. Like this. Okay, now U plus L, this is the strictly upper triangular part and the strictly lower triangular part of A. In other words, it's everything of A except for the diagonal. So U plus L is equal to A minus D. Okay, so now I'm going to probably erase these three lines for sure, and in a second I'm going to erase this line. Okay. So if I move this up here, well, if I move this up here, it's minus x a minus dx is equal to lambda x a plus dx. Okay, all I did was just move that line up there. Okay, and now I can solve this for lambda. And if I solve this for lambda, I'm going to get the following. I'm going to get lambda is equal to minus x a minus dx over x a plus dx. Okay, and I'm going to write the top. I'm going to absorb the minus sign into here to swap the a and the d around. And then when I expand, I'm going to get x dx minus x ax in the numerator. And in the denominator, I'm going to get something similar except with a plus. So x dx plus x ax. Like this. Okay, so the inner product x ax is greater than 0. Okay, so it means that this is less than x dx divided by x dx plus x ax, like this. Okay. Now this, let's see if you guys agree with this. This is less than x dx over x dx, because again, this inner product is strictly greater than 0. So we have this, and now this inequality here, or not this inequality, this is equal to 1. Okay. So this tells us that lambda is less than 1. Does that say that its absolute value is less than 1? No, it could be equal to minus 35. And this inequality would say that this inequality wouldn't dispute that. Or it wouldn't argue against that, or it wouldn't contradict that. So now what I need to do is I also need to show that it is greater than minus 1. So I need to show that it's greater than minus 1. Okay. So how can I do that? So now, what I want to do is something similar, Like I want to show that this is greater than, that this here is greater than that. In other words, if I take that away. But that's only going to be true if this is positive. Like if this is -5 not minus something is not, greater than that. Okay? So if it's -1,000 and this is 1, -1,000 minus that is not greater than minus that. Okay, but here's the thing. If we know that we have a matrix, positive definite matrix, we know all of the diagonal entries have to be equal to 0. We're going to test in the following way. A, EI, EI. Okay, well, what's happening here? A times EI, we're going to take the ith basis vector and multiply it by A. So what do we get when we take the ith basis vector and we multiply it by A? Okay, this is just going to give us the ith column of A. Then we take the ith column of A and do the dot product of that with EI. This is going to give us the A II entry. And this is less than 0. This is greater than 0. This is greater than 0 by assumption. But what is AII? AII is just a diagonal entry of the element, of the matrix. Okay, so what this shows is that if a matrix is positive definite, then all of the diagonal entries have to be greater than 0 as well. Okay. All right, so this is going to be greater than minus x ax divided by x dx plus x ax. Okay, but now what we can say is that this is going to be greater than minus x ax divided by x ax, and this is equal to minus 1. Okay, so going from here to here, one way to think about it, remember everything here is positive. I mean, this inner product is positive, all the inner products are positive. This is a negative number, so for one negative number to be greater than the other negative number, it means it's closer to 0. And so this number here, we're making a bigger denominator, so it's going to be closer to 0 in absolute value, which means it's greater since we're looking at negative numbers. Okay, so there we have that. It shows that lambda is bigger than minus 1 and less than 1. At the beginning, I said something about, I mentioned complex, that we need to show not just that its absolute value is less than 1, but its modulus is less than 1, because it could be complex. But notice this equation right here, since all of these are real things, shows that it is not complex. Lambda has to be a real number. Okay, so that's all that I want to say about that. That shows what I wanted to show, that if A is symmetric and positive definite, then the Gauss-Seidel matrix will converge. And okay, here we have it. Okay, one thing that maybe should be pointed out here is that this actually gives us a formula for the eigenvalues, and then we can actually sort of use that to give us more quantitative information about the convergence rates of some of these algorithms. We'll talk about some of that in lecture videos and also in the lab, because there's a lot of homework questions related.